In this video, we will talk about indices of dispersion. Indices of dispersion are quantities that tell us how variable our data are. To illustrate them, we will use the previous example of the 5 people who measured the height of one person using a measuring tape and producing 5 estimates for it. So these are the values we've seen before as 5 measurements of one person's height. And the question is, how can we express the variability we see, the fact that these aren't the same? Can we have a quantitative assessment of how different they are, which can be useful in answering 2 different questions? One question is, if we were to ask more people to measure the same person's height, where could we expect the new individual measurements to lie? So what kinds of additional values can we expect? The other question is, if we were to ask a completely new set of 5 people to measure this person's height and calculated the mean for that height from the new values, how far would we expect that to be from the current mean, from our current estimate based on the first sample of 5 people measuring it? So the first question has to do with individual values, and the second question has to do with indices of central tendency from new samples, new sets of values. And these questions are very important because they tell us how different answers we can get to our questions of interest, as we will see in more detail later in the course. So let us remind ourselves of this frequency display where we have each value obtained associated with the number of times it was reported. So the value 162 was reported twice, and that's why this line is up to 2. The value of 162.5 was reported once, and that's why we have the value here, and so on. As you may recall, these data have a mode of 162 centimeters because this was the value most often reported. The median is 162 because there is an equal number of measurements below and above this value. And the mean value of these measurements is 162.3 with 1 decimal digit with some rounding. So the first thing we can do about these values is to simply note how far they are in the extreme. So how far the smallest value is from the largest, and that is called the range. The range of these values is simply the difference between the largest and the smallest, and in this case, we have a range of 1.8 centimeters. This is how far apart 2 measurements can be at the extreme from this sample. The second quantity we will consider is called an interquartile range, and I will demonstrate what this means and how it is derived. The first thing we have to do, as we did for the median, is to sort our measurements in order from the smallest to the largest. Once we have our values in order, then we can assume that they form a continuum from 0% to 100%. So the beginning is at 0 and the last one is at 100%. These are the endpoints and they define the range of our measurements. Then, as we already know, the 50% point, which is the measurement in the middle, is called the median. Then we can also divide each half into half, and in this way obtain the first quarter, or first quartile as it is called, the second quarter, the third quarter, and the fourth quarter. Essentially, we are dividing our measurements into 4 intervals, such that each one has 1/4 of the available values. Therefore, between this and this point, we have half our values. This is our center, 50%. The interquartile range is simply the range that is spanned by this central 50%. So if you throw out the 1/4 smallest measurements and the 1/4 largest measurements, and you only retain the central half, the range of that half is the interquartile range. And in this case, it is equal to a 1/2 centimeter. Now, I did this with only 5 values in order to have a lot of space to illustrate, but in usual practice, we don't have 5 values, we have many more. And in those cases, it makes more sense to speak of 1/2 or 1/4 of the measurements. So for illustrations, let us consider we have a whole bunch of measurements, which you can then sort such that the first one is the smallest and the last one is the largest. And these define the range. The difference between the smallest and the largest defines the range. We can divide these into 2 halves so that the 1/2 smallest values are here and the 1/2 largest are here. And in the middle is the median. In this case, the largest value of this 1/2 is the same as the smallest of this 1/2, and this is our median. And then we can divide each 1/2 into 2 halves so that we have 4 quarters or 4 quartiles. This is the 1/4 of our data, all the smallest values, another 1/4 of our data, another 1/4 of our data, and the final 1/4 of our data, the largest value. These are, remember, these are all sorted in order from smallest to largest. And therefore, this is called the first quartile, which has 25% of our data. This is the second quartile with another 25%, third quartile, another 25%, fourth quartile, another 25%. Therefore, if we join the 2 halves, that's the middle half. If we join 2 quartiles, we have the middle half of the data. And this plus this is another 1/2 of the data. And these are the more extreme data, the smallest and the largest values. So the range within the central half is the interquartile range. And in this case, it happens to be 1.5. So the point is that we divide our data in 4 parts such that each part has an equal number of measurements. And then we define 3 points. The first quartile is the endpoint of the first quarter. The second quartile is the median. The third quartile is the end of the third quarter. And then the end of the fourth quarter is the maximum. There is, however, a different way to think about variability in the data. And this is, again, based on deviations. Deviations, if you recall, are the distances of measurements from the mean. So if we go back to our graphical display of our 5 measurements, we can also add the actual mean and its distances from the specific measurements. And as you may recall, 2 of the measurements are above the mean, and so their distances are positive. 3 are below the mean, and their distances are negative. We've gone through that when we were talking about the mean. These are the actual distances, and this is our mean. So the idea here is If there is a lot of variability in the data, these distances will be large. So the deviations will be big numbers. If all the data are close to one another, so there is little variability or little dispersion, then these deviations will be small numbers. So the idea is to try and quantify the variability by using the information from the deviations. The simplest approach would be to use the mean deviation. And the mean deviation is the sum of all the deviations divided by how many they are. And if you recall our discussion of the mean, you have already realized that this is not going to work because the sum of the deviations is defined to be 0. That's how the mean was derived. So if you just add up all those deviations, you get 0. So this idea is not going to work. Obviously, the problem is that we have some positive deviations and some negative deviations. So the easy way to deal with that is to just throw out the minus signs and end up with what we call mean absolute deviation. Absolute relates to the notion of an absolute value, which is this symbol around the deviation. And this symbol, the absolute value, means use the value without the sign, which means if there is a minus sign, throw it out. If there's a plus sign, just keep the number as it is. So by using the absolute value of the deviation, this means we only have positive numbers to add up. So this is more like what we had in mind when we were thinking about the mean deviation. This is the mean of the distances from the mean, all of them considered as positive numbers. Another trick that mathematicians like to use when they want to get rid of negative numbers is to multiply the numbers by themselves. And in statistics, this turns out to be very important because it leads us to a very useful connections between observations and probabilities that we will discuss later in the course. As you probably remember, if you multiply a positive number by another positive number, the product is always positive. But also, if you multiply a negative number by another negative number, minus times minus gives plus, so it's again a positive number. So every time you multiply a number by itself, the result is going to be positive. And the multiplication of a number by itself is called a square, and we use the symbol 2 as a superscript to mean that this number, the distance, is multiplied by itself. So using this trick, the sum of the square deviations divided by how many deviations we have is called the variance. And the variance is an extremely useful quantity in statistics. Again, what this means is we have each distance from the mean, each deviation, multiplied by itself, and these square deviations are then all added up, and the sum, the result of this addition, is divided by the number of observations, or by the number of how many of these things we have. And this is the variance. One difficulty with the variance serving as an index of variability that we can use for expectation is exactly because of the square. So in this example, all the observations were centimeters. And what we're interested in finding out is how many centimeters we can expect new measurements or new sample means to differ from the current ones. But if you multiply a deviation by itself, that would be a centimeters times centimeters, which is centimeters square. Now, square centimeters is a unit of area. It's not a unit of length or height. And it sounds very strange to express variability in height measurements by using square centimeters. it actually doesn't make any sense when you try to think of it intuitively. So the solution to this problem is actually very easy, and it is into kind of taking back this square. And how can you take back a square is by using the square root. So if you apply the square root on this number, then this kind of undoes the square. It certainly undoes it on the units. So instead of having square centimeters, you have centimeters again. And this is called the standard deviation. So this is the square root of the mean squared distance from the mean. That's what this means. And we're going to now look at this into more detail, go into it step by step, make sure we understand it. It looks a bit scary maybe because it looks like a lot of math, but it doesn't have anything we're unfamiliar with. So we're just gonna break it down into parts and see how it works. So the standard deviation. To calculate a standard deviation, we start with the values of our observations. So if we have a variable x, we start with our xi's. And in this case, I goes from 1 to 5, meaning we have 5 measurements, and these are the actual values. These are the actual measurements. The first step is to calculate the deviation. That is the distance from the mean. So from each of these measurements, we subtract the mean. And these are the differences. And then for each one of these differences, we multiply this by itself. This is what the square means. So 1.16 times 1.16 is this number, minus 0.34 times minus 0.34 is this number, minus 0.64 times minus 0.64 is this number, and so on. So these are the squared deviations, or the square distances from the mean. And all we have to do is just add them up. So if we just sum these 5 numbers, we obtain this value. This is just their sum. And then we divide by how many they are. They're 5. So divide this number by 5, and we get this number. So this is the mean squared deviation. And then if we apply the square root to this number, just enter this number into your calculator and request the square root, and you get this number. And this is the standard deviation. In fact, we use this symbol to mean the population standard deviation, as we used the Greek letter mu to indicate the population mean. We use the Greek letter sigma, the lowercase sigma, to indicate the population standard deviation. However, now we only have a sample, so the correct thing to calculate is not exactly that, it's almost like that. And the difference is we have to subtract 1 from how many measures we have. So instead of dividing with the number of observations, we divide by 1 less than that. And then this result, this number, is the sample standard deviation, which is symbolized with the Latin letter S. And this is really what we've been aiming at. This is the standard deviation that we can use as an index of variability or an index of dispersion for our set of measurements. So this formula, which does look a bit scary, is now a lot less scary because you can understand each step and the fact that it actually doesn't hide anything complicated. It just shows in a shorthand form that our index of variability is the square root of the sum of the squared distances of observations from the mean divided by the number of observations minus 1. And you'll probably never have to calculate this by hand outside of a statistics course, because that's what we have computers for. Let us now look at some examples to understand how the different indices of dispersion behave when we actually have differences in the dispersion of data. These are the data that we already have seen several times. These are our actual measurements, our actual 5 observations for one person's height. And I have created some variations on this for this illustration. So one variation is just to have some values that are closely spaced together, more closely than the actual observations. So the dispersion here is obviously smaller than here. They're all closer. So it looks like if these were 5 people measuring somebody's height, they were more in agreement about this person's height than these 5 people. And here is the opposite situation. So if these were 5 people measuring one person's height, they're not really agreeing very much with one another. So here, this is a set with higher dispersion. And here we have a hypothetical situation in which 4 of the measures are exactly the same as our actual data, but the 5th one is taken to the extreme, representing a possible mistake, like a slip of the tape. What are the indices of central tendency for these data sets? Well, the mode is the same because I have kept the 2 values at 162 in each case. The median is also the same because I've always kept one measurement less than 162 in each of these hypothetical manipulations. The mean is about the same, but not exactly the same. It's 162.3 in the original data, 0.2 in these data, 0.5 here, and 0.6. So the mean is slightly affected. So the interesting question now is, what happens to the dispersion, to our indices of dispersion? The first and simplest approach is to calculate the ranges. As you can see, these green lines here. So the range of the original data was 1.8 centimeters. The range of the second set, the more condensed set, is 1. The range of the expanded set is 3.8. And the range of the set with the one outlier is 3.3. So the range simply expresses the difference between the smallest and the largest value. What about the interquartile range? The interquartile range is not affected by where the smallest and the largest values are, because it's not affected by the smallest 1/4 of the measures and the largest 1/4 of the measures. This means that the interquartile range is much less sensitive to these manipulations. Of course, if the manipulations truly affect the nature of the entire data set, we do see it in the interquartile range. So here, where the data set is truly more condensed, we have a smaller interquartile range than the original data. And here, where we have everything more expanded, we have a larger interquartile range. In the last case, where we just have a mistaken value, an outlier, interquartile range is not affected. Let us move on to the deviation-based indices. These are the deviations, so the distances from the mean, and these are the actual numbers. The mean absolute deviation is 0.53 in the original data, 0.33 in the condensed data, 0.99 in the expanded data, and 0.94 in the data with an outlier. So you see that the mean absolute deviation is double in this set than in that, and it's 3/5 in this set than in that. And basically the difference between these two is that this triples. When you look at the standard deviation, the standard deviation of the original is 0.71, the condensed 0.42, the expanded 1.41, and the one with the outlier 1.35. So again, we see that this is about twice as much as that. And this is more than 3 times this one. And the reason that expansion costs more than is gained by condensation is that the standard deviation is made to be more influenced by larger deviations. In the mean absolute deviation, all the numbers just enter as the actual distances they are. But in the standard deviation, the numbers enter the formula after they're multiplied by themselves. This is very important. It means that a small deviation will be multiplied by a small number, that's itself. A large deviation will be multiplied by a large number itself. So the large deviations will go into the sum, having been multiplied by larger numbers than the small deviations. So they will end up influencing the standard deviation more than they would influence the mean absolute deviation. This means that the standard deviation is more sensitive to values far from the mean, which is actually a good thing for when we're interested in guessing where new values might actually lie. So to sum up our indices of dispersion, the first and simplest one was the range, which only gives us an indication of possible values we can expect. Because it only depends on 2 observations, the smallest and the largest, and because the smallest and the largest are those that will be most likely to be the result of something problematic, the range is actually sensitive to outliers, which means sensitive to any kinds of problems with our measurement. So although it can be very informative about where possible values could range, it's not really very useful when we want to guess something more precisely, where we can really expect new values or new sets to be observed. The second one, the interquartile range, gives us a good indication of the central data range of half of our data. This means that it doesn't tell us anything about the other half. This could be a bad thing if you really want to know the whole range of your data, but it is a good thing if you don't want your index to be affected by potential problems. So you can use the interquartile range to guess about a new data point that it will be within this range half of the time. If you have a good estimate for the range of half of your data that is robust and not sensitive to what happens with extreme data, then this can be a pretty good guess about new values. And you can expect that half of any additional data will lie within this range. The mean absolute deviation is not in fact very often used in practice because it doesn't really have any obvious advantages over the other options. What is frequently used when certain assumptions are met is the standard deviation. The standard deviation, as we said, gives weight to large deviations and can be very useful for predicting where new values will be. But like the mean, it is sensitive on certain assumptions about our data, about which we'll say more later in the course.